Good morning to every one of you. So we are going to continue with the part 5 of the chemical bondings, where previously we have already talked about how to use the valence bonds theory to discuss about sp3, sp2, and sp hybridizations, where in sp3 it is used to explain how four surround atoms overlap with the center atom using one of the s and 3 of the p, whereas sp2 is used to explain how three surrounding atoms overlap with the center atoms using one of the s and 2 of the p orbitals, and how sp is used to explain how two surrounding atoms overlap with center atoms using one of the s and one of the p orbitals from the center atoms. Okay, so we also talk about on how what is the shape and angles. So you have sp3 is tetrahedrals with the angle 109. sp2 has a molecular shape of trigonal planar with the bond angle 120 degree, and the sp has the molecular shape of linear with the bond angle 180. So we are going to continue on with the hybridizations inside carbon compounds. Okay, so in carbon compounds, we have possibility to form the multiple bond here. Okay, so making use of the examples in here. So we shall making use the examples such as ethane C2H6, ethene C2H4, and ethyne C2H2 to describe about the formation of the multiple bond by using the valence bond theory. Okay, so showing to you in here is the Lewis structure of the ethane. Okay, where if you look carefully in here, each carbon atom I'm going to label as C1 and C2. So each carbon in C1 is surrounded by 4 atoms in here. Therefore, this is a sp3 hybridization. Okay, whereas in the carbon in the C2, you have also 4 surround atoms here. So that is why it takes place of sp3 for the carbon atoms. Okay, whereas for the ethene molecule, C2H4, okay, as exemplified here. So this carbon is surrounded by 3, I'm going to label as usual, C1, C2. So this carbon is surrounded by 3 atoms, 1, 2, 3 in here. So therefore, this carbon takes the hybridization of sp2, whereas the other carbons also, the C2 in here also is surrounded by 3 other. So this is also sp2. Okay, and finally, this is the Lewis structure of the ethine molecule. So in ethine molecule, you have HC triple bond CH, where inside here, if you look carefully at C1 here, so C1 is surrounded by 2 atoms, therefore sp hybridizations, whereas this C2 in here is also surrounded by 2 atoms, therefore sp hybridizations. Okay. Now, note that all of them has the same center atom, which is the carbon. So therefore, they have the same ground state and same excited state, where the ground state of the carbon can be expressed as okay, 2s2, 2p2, okay, then one of the electron from the 2s is excited to 2p. So therefore, you have each of the 2s and 2p is occupied by a single electrons. All right. Okay. So hybridization, valence bond theory is used to explain on how a covalent bond is formed in here. So therefore, try to understand from the sense that if you know that it has 4 surround atom, so in the formation of sp3, all of the 1s and 3p undergoes orbital hybrid to form sp3 hybridizations. Okay, so therefore they will have the shape of a tetrahedral, as you can see in here. So if it is a carbon one, okay, so this is how carbon one are overlapping here, okay, where we call this direct overlapping. Okay, so this is direct overlapping. Okay, so not only this one, sorry, you can also have this one, direct overlapping, where it is later occupied by a pair of electrons. So all these are direct overlapping bond. So we are going to label them as a sigma bond in here. Okay, sigma bond in here. Okay, so same goes with the C2 here. Okay, Whereas in the C2, you also have 4 surround atom. So all of them are sp hybrid. So they have a shape of tetrahedral and the bond angle is 109 degree. Okay. All right. As for the ethene molecule, now in ethene molecule, since it only involves 3 surround atoms, so you are going to take sp2 hybridization, leaving one unhybrid pz orbitals in here. So I'm going to highlight with different color. So this pz is an unhybrid orbitals with a single electron in it. Okay, so the one that will undergoes sp2 hybridizations will undergoes direct overlapping, okay, as you can see inside here. So they will undergoes the sigma bond in here, okay. So you have a sigma bond in between the carbons in here, okay. So this is going to be labeled as a sigma bond, okay. This is going to be labeled as a sigma bond, okay. This is also going to be labeled as a sigma bond. So sigma goes to this, okay, and this. Okay. Now don't forget we have a pz orbitals which has one unhybrid electrons in here. So instead of direct overlapping, we shall have an unhybrid orbitals. Okay, when overlap, will form a side lapping. So this side lapping bond is also known as a pi bond in here. Okay, we call it as a pi bond. And this is how the formation of double bond is explained. So during the formation of a C double bond C, one is a direct overlapping of a sigma bond, and another one is a side lapping of a pi bond here. Okay, so it takes the shape of trigonal planar, and the bond angle in here is still 120 degrees in here. Okay, so that is for ethene molecule. All right, as for the ethyne molecule, so in ethyne molecule, you shall have one of the two S and one of the two P that undergoes orbital hybrid. Okay, so therefore it is a sp hybrid. Now leaving two unhybrid orbitals in here. Okay, you have two unhybrid orbitals in here. So each of them will become a py and pz. Okay, so now you have two unhybrid orbital where you have each occupied by single electrons. Okay. So let's talk about the direct overlapping. So the one that will form the direct overlapping will eventually form the sigma bond here. Okay, so this one will also form a direct sigma bond. Okay, whereas the second carbon C2 in here, it is already sharing with one C, and then you're sharing with another H in here to form direct overlap. Then, if you notice carefully, in here you have two unhybrid orbitals, two py and two pz in here. So each of them is going to undergo side lapping in here, where you have two pz overlap with two pz, right? It's shown to you in here. And then the two py is going to overlap with two py in here, okay? Forming another side lapping bond here. Okay, so now you have two side lapping bond. Means that you have two pi bond. So in short, we say that in between a C triple bond C in here, okay, one of them is a direct overlapping of a sigma bond, and then two of them is a side lapping of a pi bond in here. Okay? And together with the H here, which is also a sigma bond and sigma bond. So total you have 3 sigma and 2 pi in this molecule. So it takes the shape of linear and the bond angle is 180 degree. Okay. So that is how you are going to making use of the valence bond theory to explain the formation of the multiple bond inside hydrocarbons in here. Right, so now you already understand the formation of the multiple bond. So let's compare a little bit the properties of this multiple bonding in here, shall we? Okay, so in a C single bond C, okay, you shall have the bond length as 154 nanometer. In a C double bond C, you shall have a bond length of 134 nanometer. And in a C triple bond C, you shall have a bond length of 120 nanometer. Yeah, okay. So this is due to when you have more multiple bond, the bond length becomes shorter in here. Why? Because the distance between the two nuclei become closer. Okay, so when you have a shorter bond length, it indicates that you have a greater bond strength. Okay, so therefore, for breaking this covalent bond, you need a higher bond energy. That means it's going to be harder to break this bond in between C single bond C, which is the easiest to break. Okay, to the 3C triple bond 3, which is the hardest to break. Yeah. Okay. So this is how we're going to explain about the formation of the multiple bond inside an organic compound. Okay. Now, as a side note in here, not only I'm going to show you the formation of the ethane, ethene, and ethyne molecule, at the same time, I'm going to show you also the formation of the nitrogen, okay, nitrogen molecule. Okay. All right. So, are you ready? So now, this is how the Lewis structure of a nitrogen in here. Okay. And triple bond center. So nitrogen being one of our most abundant gases in Earth, okay, is basically an inert gases. Why is nitrogen an inert gas? Because it has a short covalent bond with strong triple bond. Okay, therefore it shall have a high bond energy. Okay. So this is how you are going to explain why nitrogen gas is inert, because you have a short and strong triple covalent bond with a high bond energy here. Making use of the valence bond theory, you can also make use to describe uh, how do you have these lone pair electrons present here. Okay, so we start from the ground state of the nitrogen. Okay, so the ground state of the nitrogen has 2s2, 2b3 here, 2s2, 2b3. Okay, so as usual, one of the electron from the 2s excited to 2b, in so that you make the energy level between the 2s and 2b to be equivalent. And now, because we are now talking about nitrogen is surrounded by two atoms. Teacher, what does it mean when you say that nitrogen is surrounded by two atoms? So this N1 is surrounded by one nitrogen, and this lone pair electron, we are going to assume like it is a surround atom. Okay, so that if you look carefully here, when it comes to hybridization, so since it has two surround atoms, so it will take the sp hybridization. So when there's a sp hybridization, it means that only one of the two s and one of the two p will undergo orbital hybrid in here. Okay, so you form sp, and note that inside this sp, the one of the orbitals, okay, is occupied by a pair of electrons. Okay? An electron pair. Okay? And this electron pair will later become what we so call as a lone pair electron. Okay? But it is already involved in the hybridization. In the hybridization. So, in other words, this lone pair electron can no longer be overlapped with another atom in here. Okay, so leaving this one unoverlapped in here will overlap with another nitrogen from the N2, okay, and hence form a sigma bond. And then inside here, you have 2py and 2pz, which are unhybrid. So the 2pz will be side lapping with the 2pz to form one pi bond. And then the 2py will side lapping with another 2py to form another pi bond in here. So in other words, the N triple bond N in here, okay? So you shall have one sigma bond and two pi bonds here, okay? So that is how you are going to describe the hybridizations inside the nitrogen molecules in here. Okay. Next examples that we should also see is also the nitrogen-based compound where we are going to discuss hydrogen cyanide. Okay, so inside your hydrogen cyanide, so we are going to presume that there are two center atoms, namely the carbon and also the nitrogens in here. Okay, so let's start off from the carbon in here. Now, if you look carefully from the angle of the carbon in here, so this carbon is surrounded by two atoms. Okay, so therefore this carbon take sp hybridization, and then whereas this nitrogen is similarly surrounded by two atoms, one by the carbon and one by the lone pair electron. So this nitrogen will also take sp hybridizations. All right. So as usual, we are going to start from the ground state configuration for carbon, where you have 2s2, 2p2, then it undergo excited state. And finally, because we are talking about sp hybridization, where one of the two s and one of the two p will undergo orbital hybrid in here, so therefore it forms a sp hybridizations for the carbon, okay, leaving py and pz remain unhybrid, right? So same case are going to go for the nitrogen, whereas in the nitrogen in here, so you have 2s2, 2p3, okay, where this is the ground state configuration. So in order to make energy level to be equivalent, you have excited nitrogens, okay? And finally, since only two surround atom, so one of the two s and one of the two p will undergo orbital hybrid to form sp hybridization, where inside the nitrogen, you're expected to have a lone pair electron. Therefore, one of the hybrid orbital will have a pair of electrons, leaving two unhybrid py and pz orbitals in here. So the two unhybrid py and pz orbitals from the carbon and also nitrogen here will form what we so called as a side lapping and hence form the triple bonds inside the carbon and nitrogen. Okay, so as a conclusion in here, as you can see, so carbon is direct overlapping with the hydrogen, so hence form a sigma bond in here, and direct overlapping with the nitrogen, hence forming the sigma bond, whereas the nitrogen in here will also direct overlapping with the carbon to form the sigma bond, and you have a lone pair electrons inside the nitrogens in here. Okay, so this is how you are going to describe the hybridizations inside the hydrogen cyanides. All right. Okay, so we are going to see more examples. The next examples that we are going to see in here is I also inserted if you this is from 2015 where you have the methanamide in here. So I will just briefly describe on how you can, I just briefly goes through of how the hybridization take place in the methanamide in here, where in the methanamide, as you can see from here, so this is how the Lewis structure of the methanamide, you have CONH bond in here. So how does CONH bonds in Lewis structure looks like? So it is a C double bond O and a single bond nitrogen in here. So by using the valence bond theory, we will expect students to know how to deduce what is the type of the possibility here. So this is taking of sp hybridization, sp2 hybridization, because if you see carefully, there are three surround atoms in here, and then nitrogen takes also sp3 hybridization, where you look carefully inside the nitrogen here, where you can see that inside the nitrogen atom, okay, you shall have trees around atom 1, 2, 3, and 4. Therefore, sp3 hybridizations. Okay, so then when they undergoes orbital hybrids, okay, so carbons will take sp2, leaving one unhybrid presec orbital, and this unhybrid is going to show the how is the C double bond O is formed, where one of them is forming sigma bond, and this one is going to form the pi bond inside here. Whereas the nitrogen in here is going to describe on how is the formation of the three directly overlap with the carbon nitrogen, nitrogen hydrogen, and nitrogen hydrogen, and one of them is a lone pair electron. So this lone pair electron is used to describe for this one. Okay. So this carbons takes the molecular shape of sp2 trigonal planar and with the bond angle of 120 degree, whereas nitrogen here it takes the bond angle of 107 degree, and the molecular shape in nitrogen here is no longer tetrahedral, it is a trigonal pyramidal, though it does have the arrangement similar to that of the tetrahedrals in here. So which we are going to discuss soon in here, okay? Where we are going to see on the effect of the lone pair electrons towards the bond angle in here. Are you ready? Okay. So now as you can see from the example just now, with the presence of the lone pair electron, somehow in some way, they are going to be affected by the bond angles with the presence of the lone pair electrons in here, where let's take NH3 and also H2O as examples. Okay, so this is for NH3 and this is for H2Os in here. Okay, so let's start from the ammonia. So inside the ammonia, this is a ground state configuration of 2s2 2p3. Okay, so since ammonia in here, if I draw out the Lewis structure, okay, so you shall have 4 surround atom here. Okay, so it takes sp3 hybridization. Okay, so as usual, it will undergo excited state where one of the electron excite from 2s to 2p. So it will form like this, and then when it undergoes orbital hybrid, all of the 1s and 3 of the 2p orbitals undergoes orbitals hybrid. The form of the so-called as a sp3 hybridization. And note that inside these sp3 hybridizations, one of them is already occupied by a pair of electrons in here. Okay, so with the presence of the lone pair electrons, we are going to say that because with the presence of the lone pair electron, now we have 3 possible repulsion. So this repulsion is what we call as a bond pair electron repulsion. Okay. And then we have another type of repulsions in here, which we call as a bond pair electron lone pair electron repulsion. Okay, which is actually stronger. And because of this bond pair electron and lone pair electron repulsion, it squeezed down the angle for the ammonia to make it to become 107 degree. And since it does not, but note that it still uses sp3 hybridization. I mean, it has an arrangement similar to that of tetrahedral, but because of the presence of lone pair electron, you squeeze down the angle to further, so you can no longer call it as a tetrahedral. Instead, you call the shape as a trigonal pyramidal, so with the angle 107. So inside the ammonia, as you can see, it has 3 bond pair electron and 1 lone pair electrons. So this is how we are going to describe for ammonia, right? Okay, and then as for water, okay, so water has the valence electron of 2s2 2p4. Okay, so as usual, in order to undergo orbital hybrid, one of the 2s excited 2p, so you become 2s and 2p. By the way, I forgot to draw out the Lewis structure of the water. So in Lewis structure of the water, you have 2 lone pair and 2 bond pair here. Okay, so as you can see, it takes 4 surround atom. Therefore, it is also going to have sp3 hybrid in here. So when it is sp3 hybrid, all of the 2s and 3 of the 2p orbitals will undergo orbital hybrid. And if you notice carefully inside here, two of them are already occupying the orbitals with a pair of electrons, and this is where you form the lone pair electrons inside the nitrogens in here. So when we draw the orbital overlapping diagram, okay, now we said that just now in the ammonia, we have bond pair electron repulsion. So same things goes here, which is the weakest. Okay, and then we have bond pair and lone pair electron repulsion, which is slightly stronger. So in here there are two, one is in here, one is in here, right? Okay, then if you notice carefully, we have the third type of the repulsion, which is this one. So this repulsion is called as a lone pair electron repulsion, which is the strongest among all of them. Okay, so it further squeezes down the angle. Just now, without any lone pair, you have 107. With one lone pair, you have without any electron is 109. With one lone pair electron is 107. And with two lone pair electron, it further squeezes down to become 104.5 degree in here. And because of this, the shape is no longer tetrahedral. The shape can no longer be called as a trigonal pyramidal. We call it as a band shape here. Okay, where you have two lone pair and two lone pair here, right? So as a conclusion here, as you can see, somehow in some way, with the presence of the lone pair electrons, it will cause the bonding electron angle to squeeze down further. Okay, where you have a lone pair electron repulsion is the strongest, followed by lone pair bond pair electron, which is slightly stronger, and then bond pair electron repulsion is the weakest inside here. Okay, so valence bond theory has its limitation where when it comes to the presence of the lone pair electron, it cannot effectively reduce the shape and angle for a molecule. Therefore, another theory is introduced to deduce the shape and angle of a molecule if the presence of the lone pair electron, which is VSEPR theory, valence shell electron pair repulsion theory. So what is that valence shell electron pair repulsion theory? We continue in our next video. Okay, with that, that is all for the video of this part 5. I'll see you all in the next video. Thank you.